Okay, let's dive right into this. We're going to go on a hidden journey, the incredible trip our metals take, starting from inside a single complex rock and ending up in, well, pretty much all the technology that powers our modern world.
That's right, the copper, the lead, the zinc, all the stuff that's essential for the phone in your pocket. It doesn't just come out of the ground all clean and tidy. No, it starts its life as a jumbled mess, all mixed together. Separating it is this absolute masterclass in chemistry and engineering. And it's a process that directly impacts, the cost and efficiency of all the tech we rely on every single day.
So, our story begins with a very special kind of rock. Think of it like a geological treasure chest, just packed with valuable metals, but it's locked away in a uniquely challenging puzzle.
All right, let's meet the star of our show, volcanogenic massive sulfide ore, VMS for short. Now to get this, you gotta picture the Earth millions and millions of years ago. We're talking superheated, metal-rich water just gushing from volcanic vents deep on the ocean floor. And as that searing hot fluid hit the freezing cold seawater, boom, it instantly dropped all these layers of valuable sulfide minerals, creating these incredibly rich but also incredibly complex deposits.
And what a treasure trove it is. I mean, we're talking chalcopyrite, which gives us copper, galena for lead, sphalerite for zinc. You've also usually got a ton of pyrite, fool's gold, and even little bits of precious metals like gold and silver. Basically, all the ingredients for our modern economy are sitting right here in one rock.
So, what's the catch? Because there's always a catch, right? Well, this is the crucial part. The valuable minerals are tiny, microscopic, and they're all tangled together in what scientists call fine intergrowth. It's not like picking raisins out of a cookie. It's more like trying to separate salt and pepper after they've been ground together into a superfine dust. A simple mechanical solution? It just won't work. No way.
So to solve this microscopic puzzle, engineers needed something equally ingenious. And they found it in a process that uses something surprisingly simple: bubbles.
The process is called froth flotation, and the big idea here is just brilliant. First, you brine the ore into a fine powder and mix it with water to make the slurry. Then, and this is the clever part, you add special chemicals that make only the mineral you want, let's say copper, hate water. So when you pump air bubbles through the tank, those water-hating copper particles grab onto the bubbles for dear life. They ride them all the way to the surface, creating this metal-rich froth you can just skim right off the top. It's literally a bubbly elevator where only certain minerals get a ticket to ride.
Now, chemists have two main playbooks for this process. The first is sequential flotation. That's where you run the elevator multiple times. You pick up the copper first, then you run it again for the lead, then again for the zinc, all in separate steps. But for these really complex VMS ores, it's often better to use bulk flotation. With that, you just grab all the valuable stuff at once in a bulk concentrate, and then you deal with separating them later. The choice really just depends on how tangled up those minerals are to begin with. Okay, so let's see how this all fits together into a full industrial recipe. And this isn't just one simple step. It's more like a carefully choreographed dance, designed to isolate each metal with incredible precision. First up is comminution, which is, just a fancy word for crushing and grinding the rock into that fine powder we need to free up the minerals. Next, we run the first flotation stage. Here, we're grabbing the copper and lead together, while basically telling the zinc and pyrite to stay put. After that, we take that copper-lead mix and separate those two from each other. And finally, we go back to what's left in the tank, wake up the zinc, and float it to get our third and final product. And the level of control here is just remarkable. One of the key variables they play with is pH. Chemists will carefully adjust the water to make it alkaline, often to a pH between 10 and 12, which is kind of like a mild bleach solution. And this alkaline environment is absolutely key. It helps to naturally suppress minerals like pyrite, convincing one tiny particle to float while its neighbor right next to it sinks. And that tiny difference? It can be worth millions of dollars.
So how do they actually tell the minerals what to do? The real magic of flotation isn't just the bubbles, it's a sophisticated chemical cocktail. You can think of them as tiny little traffic cops in the water, directing each and every mineral particle exactly where it needs to go.
So let's open up the chemical toolkit. First, you have collectors. Think of these as sticky hands that coat the mineral you want and help it grab on to an air bubble. Next up are depressants. These are like putting little do not disturb signs on the minerals you don't want to float, making them love water so they stay behind. And finally, you have activators. These are like a wake-up call for a mineral you previously told to stay put, getting it ready for its turn on the bubbly elevator.
And here is a perfect example of that wake-up call in action. This is where it gets really, really clever. So after the copper and lead are gone, the zinc mineral, sphalerite, is still sitting at the bottom of the tank with one of those do not disturb signs on it. So the chemists add some copper sulfate. This simple chemical basically rips that sign off and prepares the sphalerite's surface so the collectors can attach. And just like that, it's finally ready to be floated and collected. It's an incredibly elegant chemical solution.
Now this process is brilliant, for sure, but the industry is always pushing forward. They're constantly facing down these old challenges with brand new technology, trying to make mining even more efficient and sustainable.
And just to understand the scale of this challenge, consider this number. In some of the most complex ores, a single particle of galena, that's the lead mineral, can be just 12 micrometers across. For comparison, a single human hair is about 70 micrometers wide. So we are manipulating particles that are nearly 6 times smaller than a strand of your hair. It's just wild.
So that's the fundamental question that's driving all the innovation, right? How do you get even better at separating these microscopic, interwoven particles, all while using less energy and hopefully fewer harsh chemicals?
And the industry is finding some incredible answers. Things like smarter sorting with X-rays that can identify and just chuck out worthless rock before you waste a ton of energy grinding it. They're designing flotation columns that are way more efficient than the traditional tanks. Researchers are developing greener chemical reagents to replace toxic ones like cyanide. And some are even exploring using microbes, bacteria, to literally eat the metals out of low-grade ore. How cool is that?
So where is all this heading? Well, it points toward a pretty fascinating future, and it leaves us with a final thought to chew on. What if we could refine this science to the point of perfection? What if we could design chemical keys so precise that they only unlock one specific metal at a time, leaving everything else completely untouched? I mean, that's the ultimate goal, isn't it? Turning a complex, jumbled-up rock into pure elements, creating a perfectly efficient circular process for the materials that build our entire world.